In 1960, an astronomer named Frank Drake pointed a radio telescope at two nearby stars and listened. He was not looking for anything specific. He was looking for something that should not be there, a pattern that nature could not have made, a signal buried in the noise of an indifferent universe. He heard nothing, or rather, he heard everything that could be explained. The static of cosmic gas, the hiss of charged particles, the ordinary radio breath of a galaxy going about its business. Nothing that required another mind to produce it. He listened for 4 months. Then he stopped. And the question that had been sitting beneath that entire effort, the question that has now been sitting unanswered for more than 60 years, is one of the most unsettling in the history of science. Not, are we alone? That question is too simple. The real question is this: if other civilizations exist, and the mathematics suggests they should, and if some of them have had billions of years longer than we have to develop the means to reach across the void, then why, in 6 decades of searching, have we received nothing that requires another intelligence to explain it? Why does the sky remain silent? And more troubling still, is the silence telling us something about what happens to civilizations, including ours, when they reach a certain point? At first glance, the silence feels like absence. It feels like evidence of nothing. But the history of that silence is not static. It has been accumulating context, and the context, examined carefully, suggests that the silence is not empty at all. It may be full of something we have not yet learned to hear. The original SETI programs, the search for extraterrestrial intelligence, were built on a particular assumption. That assumption was reasonable for its time. It went something like this: we are a young technological civilization. We have just learned to transmit radio signals into space. If another civilization exists and is at roughly our level of development, they would likely do the same thing. They would build radio telescopes. They would transmit signals, and the signals would travel outward at the speed of light until something intercepted them. The job, then, was straightforward. Point large radio dishes at nearby stars. Listen for patterns in the radio spectrum that nature could not explain. Wait. Frank Drake even worked out which frequency to use. He identified a narrow band in the radio spectrum, a region where the galactic background noise drops to its lowest, bracketed on either side by the natural emission lines of hydrogen and hydroxyl. Drake called it the water hole. He imagined that any civilization smart enough to transmit an interstellar signal would also be smart enough to identify this quiet window in the cosmic radio noise and use it as a natural gathering point, a universal meeting frequency. All we had to do was tune in. 6 decades of listening later, the water hole has delivered nothing. That result is not nothing. It is evidence. And what it may be telling us is not that the universe is empty, but that we have been listening the wrong way. A researcher named Ben Zuckerman has spent decades thinking about this problem. He has watched SETI strategies evolve, seen the assumptions shift, and has recently laid out a case for why the field needs to update its core thinking. Not just its technology, but its imagination. And the update he proposes is unsettling in a specific way. Because when you follow the logic, you arrive at a picture of our place in the cosmos that is both more hopeful and more disturbing than the original assumption suggested. The argument begins with a simple observation about time. If other civilizations exist in our galaxy, almost none of them will be at our level of development. Here is why. The Milky Way is roughly 10 billion years old. Technological civilizations, assuming they exist, could in principle have been emerging for most of that time. We have been a technological civilization, by any generous definition, for roughly 100 years. That makes us, at best, the youngest 1% of any civilization that has ever existed. If the typical civilization survives for even 10,000 years after developing the ability to send detectable signals, then 99% of them would be more advanced than we are. If the typical civilization survives for 1,000,000 years, the gap between us and the median civilization becomes nearly incomprehensible. We would not be slightly behind. We would be children, looking up at adults who have had entire geological epochs to develop capabilities we have not yet imagined. This matters because the original SETI programs were designed to find civilizations that think like us. They assumed aliens would use radio because we use radio. They assumed aliens would transmit at certain frequencies because those frequencies seem logical to us. They assumed the signals would look a certain way because that is the kind of signal we would send. But if the civilizations most likely to be out there are millions of years ahead of us, then designing our search around what we would do is not a strategy. It is a projection. It is like a civilization that has just discovered fire, trying to detect a civilization with nuclear power by looking for larger campfires. So what would a civilization millions of years more advanced than us actually do? That question is the center of everything. And the answer, or at least the beginning of an answer, starts not with radio, but with light. The fundamental problem with radio transmission across interstellar distances is geometry. A radio signal, even from the most powerful transpiller we can imagine, spreads. It does not travel as a tight beam. It fans out across space, thinning with distance, until the energy per unit area becomes vanishingly small. To send a radio signal strong enough to be detected across even 100 light years, a civilization would need either an enormous amount of power or an enormous transmitting array, one with a baseline measured in thousands of kilometers. We have built arrays at that scale. But even then, the signal arriving at a distant star would be so diluted across space that detecting it would require extraordinary sensitivity. The original workaround was elegant in its simplicity. Instead of spreading power across all frequencies, concentrate it into a single extremely narrow band, a spike in the spectrum. Nature rarely produces narrow spikes in radio frequencies. A spike would stand out like a voice in an otherwise empty room. This is the logic behind the waterhole strategy. Pile all your transmission power into one frequency. Make the spike tall enough above the galactic background to be unmistakable, and wait for someone to notice. It has not worked, but there is another option, and physics has been pointing at it for a long time. Visible light and near-infrared radiation behave differently from radio. The key difference is collimation, the ability to form a tight beam. The tightness of a beam is fundamentally limited by the wavelength of the radiation being used relative to the size of the transmitter. Radio waves have wavelengths measured in centimeters to meters. Visible light has wavelengths measured in hundreds of nanometers. That difference, a factor of tens of thousands, means that an optical transmitter of the same physical size as a radio transmitter can produce a beam tens of thousands of times tighter. The energy, instead of spreading across a volume of space large enough to swallow entire solar systems, can be directed with extraordinary precision. A laser array, 1 meter across, using modern technology we already understand in principle, can produce a beam as tight as the one our 1,000-kilometer radio array barely manages. And if you build a laser array at the 1,000-kilometer scale, a space-based interferometer, say, orbiting in formation, you do not flood an entire star system with signal. You can illuminate a single planet. This changes the geometry of the search entirely. It means that an advanced civilization does not need to broadcast power in all directions, hoping something intercepts it. It can target. It can aim. It can send a signal to a specific world around a specific star and deliver it with the efficiency of a precision instrument rather than a lighthouse. But targeting requires knowing where to aim. And 60 years ago, we did not know where to aim. We did not know whether other stars had planets at all. The existence of exoplanets was speculative. The idea that Earth-sized worlds might be common around sun-like stars was a hope, not an observation. Then came decades of planetary detection work. culminating in surveys that revealed something that changed the calculation permanently. Planets are not rare. Planets are ubiquitous. Essentially, every star appears to host a planetary system of some kind. Earth-sized planets in the habitable zones of sun-like stars appear to be common by astronomical standards, rare enough that we have not yet resolved individual examples with certainty, but statistically guaranteed to exist in enormous numbers within the galaxy. If we are this close to being able to identify the inhabited worlds in our neighborhood, and within the next decade or two, direct imaging technology may allow us to see continents, oceans, the chemical signatures of living biospheres on planets orbiting nearby stars, then a civilization millions of years ahead of us has almost certainly already done this. They have mapped the local inhabited worlds. They know which planets bear life. They know which planets bear something more than life. Zuckerman's point cuts here like a blade. An advanced civilization in the local region of the galaxy would not be searching blindly. They would already know that Earth, life, our biological signals, the oxygen in our atmosphere, the seasonal fluctuations in our spectral profile, the chemical signatures of a living world, have been visible to anyone with sufficiently advanced instruments for hundreds of millions of years. Our radio signals, the ones we have been broadcasting for a century, have now reached stars within roughly 100 light years of us. But the evidence of our biology has been traveling outward for far longer. If anyone is looking, they know we are here. That possibility deserves a moment to sit. Because if an advanced civilization knows we exist, and they have the capability to target a single planet with a collimated signal, then there is a scenario worth confronting. The signal may already be there. It may have been arriving for years, decades, perhaps longer. And if it is not arriving in the radio frequencies we have been monitoring, if it is arriving instead as a pattern in optical or infrared wavelengths that we have not been systematically searching, then all of those years of radio silence have been the equivalent of pressing your ear against the wrong wall. The scenario that emerges from Zuckerman's analysis is not that the universe is empty. It is that we have been running the wrong search for 60 years. And that conclusion carries a particular kind of weight. Because if the search has been wrong, if the signals have been arriving in channels we were not watching, then we do not know how long we have been missing them. We do not know what we have already failed to hear. This is where the search begins to change. In the past decade, a new approach has quietly been gaining ground. It goes by the name of commensal seti, a term borrowed from biology, where it describes a relationship in which one organism benefits from another without affecting it. The idea is straightforward. Rather than building dedicated radio observatories and pointing them at individual star systems, one at a time, looking for narrowband signals in the water hole, piggyback the search onto the astronomical surveys that are already happening. Use the data already being collected and look for anomalies anywhere, not just in radio frequencies, not just in the directions we expected, not just in the patterns we anticipated. The surveys that now exist or are about to begin operation are unlike anything the original SETI programs could have imagined. Consider the Rubin Observatory in the mountains of Chile. It is about to begin a 10-year survey of the southern sky, imaging the entire observable southern hemisphere every 3 days for a decade. The camera attached to it is the largest ever built for astronomical purposes. The data flow is approximately 20 terabytes per night, more information than a human being could meaningfully process in a lifetime, arriving every single night, continuously, for 10 years. The purpose of this survey is not to look for alien signals. It is to track supernovae, map dark energy, catalog asteroids, chart the structure of the local universe. But in doing all of that, it will produce the most sensitive, most complete domain map of the southern sky ever constructed. And any object that changes in an unexpected way, any light source, that brightens or dims in a pattern, inconsistent with known natural processes, will be flagged by automated systems and sent to teams of researchers for analysis. The point is that an optical or near-infrared laser signal from a civilization 100 light-years away, aimed at Earth and modulated in any of the ways that would mark it as technological in origin, might be exactly the kind of anomaly the Rubin system is designed to catch. Not because anyone designed Rubin to find aliens, but because what makes a signal alien, the unexpectedness of its behavior, is precisely what these systems are tuned to detect. Research teams have already begun working out how the Rubin alert pipeline could be adapted to flag potential technosignatures. The infrastructure exists. The data will exist. The question is whether anything in the data warrants a second look. And then there is the square kilometer array. Radio was not abandoned. It was scaled. The SKA is a radio telescope being assembled across 2 continents, South Africa and Australia, in an architecture of thousands of individual antenna elements spread across distances measured in thousands of kilometers. When complete, it will function as the most sensitive radio telescope ever built. Its data collection rate will exceed everything previously constructed by an almost incomprehensible margin. Where the Rubin Observatory collects 20 terabytes per night, the SKA will collect equivalent volumes every few seconds. At that scale, the computational challenge of finding alien signals is almost indistinguishable from the challenge of not drowning in information. Research teams are developing algorithms, many of them drawing on machine learning approaches, to process the incoming flood in real time, flagging events that match signatures of interest before the data can even be fully written to storage. The SKA does not make the search easy. It makes the search possible at a scale that changes what possible means. If radio signals of technological origin exist anywhere within a vast volume of the galaxy, the SKA may have the sensitivity to find them. But there is a subtler implication hiding in all of this, and it is the one that most changes the nature of the search. We are not just getting better instruments. We are getting better at understanding what we have been looking for. For decades, the implicit assumption of SETI was that a technological civilization would transmit signals deliberately, intentionally, with the purpose of making contact. The civilization would decide to send a message. They would build a transmitter. They would choose a target. The signal would be an act of will, a decision, a deliberate
reaching out across the void.
And so, the SETI programs listened for that kind of signal, something intentional, something designed to be recognized. But there is another possibility that has been gaining attention. A civilization that is sufficiently advanced might not be transmitting intentional signals at all. It might simply be using powerful technology for its own purposes. Energy collection, computational infrastructure, internal communication, industrial processes. And some of that technology might leak signals into space as a byproduct, the way our own civilization leaks radio signals, not designed for anyone to hear, but detectable if you are close enough and sensitive enough. The signatures of such a civilization might not look like a message. They might look like an anomaly, a star that dims in the wrong way, a planet that emits the wrong wavelengths, a region of space where the infrared signature suggests something absorbing starlight and radiating it as waste heat in a pattern that natural processes cannot account for. Technosignatures, not radio messages. Evidence of engineering, not communication. This shift from looking for intentional messages to looking for evidence of the existence of technology is perhaps the most important conceptual change in the history of SETI, because it removes the requirement that another civilization want to be found. It only requires that they exist. And if we accept that some civilizations in the galaxy may have had billions of years to develop, then the evidence of their existence might be written not just in signals, but in the structures of the galaxy itself. in the distributions of stars, in the thermal signatures of entire regions of space, in the long-term reshaping of resources that a civilization operating at planetary, stellar, or even galactic scales might leave behind. We may already have this data. It may be sitting in archives from surveys conducted decades ago. The question is whether we know what we are looking for when we look at it. Researchers have begun the project of searching archival astronomical data specifically for signs of technology. The European Southern Observatory's HARPS program, originally designed to detect exoplanets by measuring tiny Doppler shifts in starlight, has been reanalyzed by teams looking at whether the same observations might have captured laser communication signals from planets around those stars. Nothing has been found yet, but the approach demonstrated something important. Much of the data we already have may be sensitive to the kinds of signals Zuckerman and others predict advanced civilizations would produce. We have been taking observations that could detect alien technology without realizing that is what they could do. The question of what an alien signal would actually look like has no definitive answer. But researchers have identified certain features that would be difficult for nature to produce. A signal that arrives with Doppler characteristics consistent with a planetary orbit, slightly varying in frequency, in a regular cycle as the transmitting world moves toward and away from us, would have a natural signature that distinguishes it from background sources. A signal that appears across multiple wavelengths simultaneously, or that shows patterns of modulation not generated by any known astrophysical process, or that has a statistical structure inconsistent with noise. Any of these would warrant serious investigation. Nature is creative. It produces pulsars that pulse with the regularity of clockwork. It produces molecules in space that nobody predicted. It produces phenomena that look on first encounter like they require an explanation beyond physics. The history of astronomy is partly a history of initially mysterious signals that turned out to have natural explanations. But not every signal will have one. The WOW signal of 1977 remains unexplained. A burst of radio emission lasting 72 seconds, matching the expected profile of a narrowband artificial transmission from the direction of the constellation Sagittarius, recorded by a researcher named Jerry Eman, who wrote the word WOW in the margin of the printout, has never been detected again, never been replicated, never been explained as a natural phenomenon, and never been confirmed as artificial. It sits in the middle of the radio telescope data from that night, almost 50 years ago. A single anomaly in decades of searching, waiting for a context that has not arrived. That is the texture of the silence. It is not perfectly empty. It contains fragments, hints, events that briefly suggested something and then refused to confirm themselves. The silence is not the silence of a room that has never been occupied. It is the silence of a room where something may have moved once and then was still. Here is where Zuckerman's argument reaches its most pointed conclusion, and it is worth following carefully. He is not arguing that we will definitely find signals if we update our strategies. He is arguing that our previous strategies were not good enough to rule out the existence of signals. 60 years of radio listening at the waterhole, with the sensitivity of instruments available in that era, pointed at a small number of targets, looking for a specific kind of signal. This does not constitute a thorough survey of the possibility space. It constitutes a limited search of one small corner of it. The failure to find a signal in that corner does not mean the room is empty. It means that corner, specifically, has been checked. The possibility space that has not been checked is larger than the one that has. When Zuckerman estimates a target list for a next-generation search, he focuses on sun-like stars within roughly 650 light-years, a distance that feels arbitrary but represents a reasonable definition of local, a small slice of our galaxy's 100,000 light-year radius. Within that range, Statistical projections derived from the Kepler mission suggest there may be tens of thousands of potentially habitable planets around Sun-like stars. Of those, a conservative estimate of a few hundred might resemble Earth in multiple relevant characteristics. Not because we know how Earth-like a planet needs to be to produce a civilization. We do not know that. But because starting conservative is the right approach, when the consequences of being wrong in either direction are so different. If we search conservatively and find something, we have found something. If we search conservatively and find nothing, we have learned something about that conservative definition of the target space. What we cannot afford is to not search at all, or to search with tools and strategies that were designed for a different understanding of the universe. One that predates our knowledge of planetary systems, of laser technology, of the scale and sensitivity of modern astronomical surveys. This is the place where the discussion of alien signals meets something more personal. We are a civilization that has been able to transmit signals into space for approximately 100 years. In that same time, we have also developed the capacity to do things that previous centuries could not have predicted. Not just radio telescopes, but nuclear weapons, genetic engineering, artificial intelligence systems, of a kind that were science fiction a generation ago. We are in the middle of a period of extraordinarily rapid technological development, and the question of what happens next, whether we continue to develop, plateau, collapse, or transform into something that our current selves would not entirely recognize, is not separate from the question of alien signals. It is the same question. Because if the Milky Way contains even a small number of civilizations that have survived for millions of years, then survival at that timescale is possible. Something allowed them to persist, and if the galaxy is silent, if no signal, technosignature, or evidence of astronomical engineering has been clearly identified, despite 60 years of search, despite the observatories now being built, then there are a limited number of explanations. 1. We are genuinely alone, or nearly so. The emergence of technological civilizations is so improbable that we may be among the first to exist in this galaxy, separated from others by distances so vast that no signal has reached us yet, and perhaps none ever will. 2. Civilizations exist, but they are silent, by choice, by physics, or by nature of what they have become. Perhaps sufficiently advanced civilizations do not transmit. Perhaps they use technologies that leave no detectable footprint. Perhaps they have gone inward, retreating into computational substrates, living in clusters where energy can be used with maximum efficiency and no information need leak into the surrounding void. 3. Civilizations emerge but do not persist. Something stops them. Some transition that all technological civilizations reach proves fatal, or nearly so, a filter, an event horizon through which complexity passes in one direction but not out the other. The silence of the sky does not tell us which of these is true, but it tells us something about probability. If we are not alone, and if the silence is real and not merely a failure of our instruments, then the universe has been conspicuously quiet for reasons we do not understand. And among those reasons, the one that carries the most weight, not the most certain, but the most consequential, is the possibility that what we are searching for does not exist because it cannot exist. That something systematically ends what we are becoming before it can become what we are searching for. That possibility is called the Great Filter, and it sits somewhere in the sequence of steps between the formation of a rocky planet and the emergence of a civilization transmitting signals across interstellar distances. Either we are past it. The filter is behind us in the deep history of life's improbable emergence from chemistry, or it is ahead of us, waiting at a transition we have not yet reached. The silence cannot tell us which, but it insists that one of these is true. The great observatories coming online in this decade and the next, the Rubin Observatory, the Square Kilometer Array, the Habitable Worlds Observatory, and the instruments that will follow it, the space-based interferometers that may one day resolve the continents of planets orbiting other stars. These are not just scientific instruments. They are the means by which our civilization will, for the first time in history, conduct a search of the universe that is sophisticated enough to begin producing a real answer. Not a definitive one, not a certain one, but a real one. If after a decade of Rubin data, after years of SKA sensitivity, after the first direct images of nearby Earth-like worlds, we have still found nothing, no signal, no anomaly, no technosignature, no evidence of engineering, that result will itself be a finding. It will push the probability that technological civilizations are rare to a level that demands a different kind of attention. Not the attention of SETI astronomers, but of everyone. Because a galaxy this old, this long, this chemically fertile, this full of suitable worlds, that contains only one technological civilization, ours, is a galaxy is telling us something about the rarity and the fragility of what we are. And if we do find something, a pattern in the infrared, an anomaly in the time domain data, a Doppler modulated signal in an unexpected frequency range that resists every natural explanation offered to it, that result will demand an even different kind of attention, because it will mean the silence was not empty. It will mean something was there all along, waiting in the data, and we were not ready to see it. There is a version of this story in which the signal is already in the archives, in which it arrived years ago, was recorded faithfully by an instrument doing something else, and sits in a database, somewhere waiting for the right algorithm to notice it, in which the question, is anyone out there, has already been answered, and the answer is waiting on a hard drive in a research institution unread. That possibility is not science fiction. It is a genuine implication of the commensal SETI approach. The data exists. The signal, if there is one, may exist inside it. 65 years ago, Frank Drake listened for 4 months and heard nothing. The question was not closed. It was opened. Everything that has been built since, the larger dishes, the wider surveys, the faster algorithms, the orbital observatories, the laser detectors, the infrared cameras, the machine learning systems trained to notice what humans overlook. All of it is the long, slow answer to the question he first asked in a quiet control room in West Virginia, at a telescope pointed at stars that did not answer. The sky is still quiet, but for the first time in the history of the search, we have instruments capable of asking the question in a way the question deserves. And what we do not yet know, what may already be waiting in the data we have already collected, or may arrive in the data we are about to collect, or may never arrive at all, is not merely whether another mind exists somewhere in the dark. It is what the answer will mean for us, here, now, at this specific and apparently improbable moment in the life of a civilization that is only beginning to understand how unusual it might be. The signal, if it exists, is already out there, moving at the speed of light, either toward us or not. We have never been better equipped to find out which, and we have never had more riding on the